Now we have to deal with the cases where n does not equal 2 or more. This equation was only true for n equals 2 or more. This was the original equation we had. You notice that there's an n equals 0 term here and an n equals 0 term here, none here. So we have to deal with that. So if n equals 0, we have an n equals 0 term here, which is 2 times a sub 2 x to the 0, which of course is 1. And then we have an n equals 0 term here, which is k plus 1 a sub 0 x to the 0, which of course equals 1. And we can solve for a2 in terms of a0. Now don't forget, a0 and a1 are unknown because it's a second degree equation. We're going to have two unknown constants. So finally we get a2 equals minus k times k plus 1 a0 over 2. What about the n equals 1 case? The n equals 1 case, we do the same thing, except we're going to have three pieces. We're going to have an n equals 1 piece here, none here, 1 here, 1 here. So we're going to have three n equals 1 pieces. N equals 1, we're going to have 3 times 2 is 6, a sub 3, x, the first, of course, minus, there's no contribution from this one, but there's a contribution from this one, which is, of course, a sub 1, x to the 1, minus 2, a sub 1, x to the first power. And then we're going to have a contribution here, which is, of course, k times k plus 1, a1, x to the 1 equals 0. And solving this for a3 in terms of a1, the coefficient, of course, of x1 has to be 0, so we can throw away the x1, and we finally get a sub 3 equals 2 minus k times k plus 1 over 6 all times a1. So if we're given a0 and a1, we can find a2 and a3. And you'll notice that a0 and a2 are related, a1 and a3 are related, and what's going to happen, of course, is a3 and a5 are going to be related by this equation, and a2 and a4 are being related by this equation. So you have the polynomial separating into two pieces, one which is of even powers and one which is of odd powers. Now, this is the important part. We have to pick the k's. If we pick k is 0, you'll notice that a2 is 0, therefore a4 is 0, etc. And we're not interested in this piece here, which is going to go on forever. There are two kinds of solutions. There's the odd and even solution. So we're going to pick the even solution when k is 0. When k is 1, we're going to pick the odd solution because that will give us a finite polynomial. When k is 2, we're going to pick the even solution again. So in each case, we're going to get a finite polynomial. These polynomials are called the Legendre polynomials. Now time to calculate some of the Legendre polynomials. As you recall, for even k, we're going to have even polynomials that truncate. For odd k, odd polynomials that truncate. There's always another solution, but we're not interested in those other solutions. So when k is even, there is an odd solution, but doesn't truncate. It's infinite. It goes on and on forever. And the same is true for the odd case. There's an even polynomial that we're not interested in. So let's let k equals 0, and we're going to label this p0 of x. So that's the k value. It's the very first Legendre polynomial, the 0 Legendre polynomial. Now, we're only interested in the even term, so let's go and calculate a2. Well, you'll notice that a2 is just 0 times a0, and since a2 is 0, a4 will be 0, a6 equals 0. All the even ones are 0, and therefore we have p0 of x just equals a0 equals a constant. What about P1 of x, k equals 1? Well, we're going to go to this equation to see what A3 is. Don't forget A0 and A1 are not given. Those are the two constants we don't know. And if you look at k equals 1, you have 1 times 2 is 0. Excuse me, it's 2. 2 minus 2 is 0, so A3 is 0. And therefore, by this equation, A5 is 0, A7 is 0, etc. And therefore, P1 of x is just A1 times x. All the A3, A5, A7 terms are not there. What about k equals 2? K equals 2, we're going to go up to this equation, and we're only looking for the even terms. A2 is minus 2 times 3, 6 divided by 2, 3A0. So in this case, A2 is minus 3A0. Now what about A4? Well, we're going to plug in, k is 2, but when we plug in 2 into this equation for n to get A4, we notice that A4 is 0. And once A4 is 0, A6 is 0, etc. And so we just have P2 of x is A0 minus 3A0 x squared. And we can rewrite that as A0, 1 minus 3x squared. And that's the P2 up to a constant. And we can find P3 and P4 and P5 the same way. We will use this equation here. We'll start for example, for P3, we'll find A3, and then we'll find A5, etc. Now it turns out that A5 is going to be 0, and so it only has 2 terms again. And we can generate all the rest of the Legendre polynomials that way. And they have some very interesting properties, and we'll get to that in the next session.